Hello everyone, my name is Yiguang. I am a third-year PhD student in the Computer Science Department at Columbia University. This work, Chasm Under the Glass Ceiling, Explaining and Reproducing Disparities in Homophilous Networks, is jointly done with Jesse from MIT, Igika and Pri from the Journalism School at Columbia University, and Augustine, my advisor in the Computer Science Department at Columbia University. In the past studies, people find that in networks with a minority and a majority community, minorities are often underrepresented at the top of social hierarchy. There are articles saying that females are underrepresented for high-paid jobs, African Americans are underrepresented in some education system, and women are underrepresented in STEM fields. This phenomenon is referred as the glass ceiling effect, and it describes that there is an invisible ceiling that stops the minority from reaching to the top level of the social hierarchy. If we take the social hierarchy as x-axis and the ratio of minority as the y-axis, we can first draw a horizontal dashed line that represents the overall ratio of minority in the entire society. The glass ceiling effect says that in the very top social in the very top social hierarchy, the ratio of minority is below its overall ratio. However, researchers are less clear about the representation of minorities from lower levels of the social hierarchy, which contains most of the population. Would the ratio decrease monotonically, or would the ratio stay flat in the lower level of social hierarchy? Or maybe there's no clear pattern in lower level of social hierarchy. Indeed, in this project, we offer a more complete picture of social disparities at each social level with empirical evidence. And we show that the minority representation exhibits two opposite phrases. At a higher rank of social ladder, the representation of minority community decreases, but lower in the ladder, the representation of minority increases. We refer to this oppositing phenomenon between the upper level and lower level as the chasm effect because people who observe the lower or upper layer of the hierarchy may agree that there is a systematic bias present, but will claim it is in the opposite directions. This project has four main contributions. First, we show the existence of chasm effect with empirical evidence from real-world datasets. The empirical evidence shows that the ratio of the minority community does not decrease monotonically as we move up to the hierarchy. We then analyze the interaction among network growth mechanisms and derive the necessary mechanisms for both the chasm effect and the glass ceiling effect to be present in bipartite networks. We then propose a complete bipartite bi-affiliation network growth model that generalizes the necessary mechanisms, and we show that the generalized model is capable of reproducing real social networks. Finally, we provide two real-world applications of our findings. Specifically, they are job advertisement and fact-checking. We show that the chasm effect could impact the direction of bias and thereby motivating the importance of considering chasm effect. Let's first talk about empirical evidence. We have two datasets in the project. The first one is TensorQQ, which is one of the most popular instant messages for group chats in China. This dataset contains about 274 million users and 58 million groups. The average ratio of female members in a group is about 41%. We see that as group size increases, the average ratio of female members first increases, then decreases. The similar traits can be found in the WhatsApp datasets as well. WhatsApp is one of the most widely used messaging apps around the world. This dataset contains 2,000 groups around political conversations and about 205,000 unique users. For each group, we label it as either pro-BJP or anti-BJP. The ratio of anti-BGP groups in this dataset is about 28%. And we again see that the average ratio of anti-BGP groups first increases, then decreases as group size increases. Indeed, the chasm effect is not unique to bipartite networks. We observe in a projected QQ membership network as well as in an Instagram network that the ratio of female connections a member has first increases, then decreases. This common pattern shared by networks of different types as well as networks focusing on different contexts indicates that there may be some simple structure patterns that are not well explained in the existing literature. So we want to analyze the mechanism that can lead to our observations. We primarily focus on group member networks as they are not studied but have many applications. We model them as bi-affiliated bipartite networks, where the network is partitioned into groups and members, and each member and each group has a viewpoint that favors the minority or majority. We color groups and members that has a minority view as red, and otherwise we color blue. In order to talk about advantage or disadvantage of the minorities, we have to agree on a measure of success for social hierarchy in a social network. Following the conventional approach that sees networks edges as the network's social capital, we define successful groups in a group member network to be groups with more members, and active members to be the ones that join more groups. We assume the following mechanisms, which are widely applied in previous network models. The first one is homophily, which says members tend to join groups of their own affiliation. And second is rich get richer, which says currently active members are likely to join more groups than current inactive members. And larger groups are likely to have a higher growth rate than smaller groups. The third mechanism we assume is equal chance, which allows members to join groups uniformly at random. Since the rich get richer mechanism and the equal chance mechanism cannot be applied to each other, we have three possible combinations of the three mechanisms. Specifically, they are selective homophily on rich get richer, selective homophily on equal chance, and the general homophily, where homophily can be applied to both rich get richer mechanisms and the equal chance mechanism. We then test each of them in a simple homophilous model to be introduced in a few slides. For selective homophily on rich get richer, we can have both glass ceiling and chasm effect to occur, but none of them would occur if it is for selective homophily on equal chance. And for general homophily, only glass ceiling effect can occur. So it seems like the equal chance mechanism does not really play a role in terms of generating the chasm effect. So we also test the case when there's no equal chance mechanism at all. And we see that in that case, only glass ceiling effect can occur. So we conclude two necessary mechanisms for both the glass ceiling effect and the chasm effect to occur. The first one is we must have homophily on rich get richer mechanisms, and the second one is the existence of equal chance mechanism. Now let's talk more about the model in details. We first initialize the bipartite network with one red member connecting to one red group and one blue member connecting to a blue group. At time t, the network grows as the following. First, it can have member growth with probability alpha. In that case, a new member joins the networks and the member is colored red with probability R and blue with probability 1 minus R. Otherwise, with probability 1 minus alpha, we randomly pick an existing member with probability proportion to the member's degree. Then this chosen member can either go into group growth or a connection growth. With probability eta, the member creates a group of the member's own color. And with probability 1 minus eta, the member joins an existing group according to one of the following two steps. The first one is rich get richer with homophily. With probability C, the member picks a group with probability proportion to the group's degree. And if the color of the group is the same as the color of the member, then the member joins the group directly. Otherwise, the member would accept the connection with probability rho. If the member does not accept the connection, then the member restarts from the beginning of connection growth until a new connection is built. Otherwise, with probability 1 minus C, the member uniformly picks a group at random and just join the group directly. So the next question we ask is, can this model reproduce the real social network? The answer is yes, and with a generalized model, specifically to allow more degrees of freedoms and therefore to reproduce real social networks. We extend the simple homophilous model with selective homophily on rich-get-richer mechanism to a generalized model. In this generalized model, we allow different homophilous levels for the rich-get-richer mechanism and the equal chance mechanisms. The numerical simulations generated through this generalized model can well capture both the chasm effect and the glass ceiling effect observed in empirical datasets. With this generalized model, we can prove many theory results, and the notations here are complicated due to time limits. We only introduce the conclusion here. We can show that group size distributions follow power laws, and member degree distribution also follow power laws. We can provide the sufficient and necessary condition for the glass ceiling effect to occur, as well as the sufficient and necessary conditions for the chasm effect to occur. Once the chasm effect occurs, we can localize the group size at which the group ratio changes its monotonicity. Having all those said, does chasm effect matter in real life? And here we provide two applications. The first one is job advertisement. Currently, employers post job opportunities online, which provides an additional advantage to the receivers. We test an advertising strategy with a QQ dataset to see the fairness of this strategy. Considering the advertising strategy that places ads to groups larger than a threshold, we see as the threshold gets lower, the advertising strategy changing from favoring males to females in terms of member exposures. Specifically, if the advertisements are placed to groups with size larger than 80, then among all the receivers, there are 39% of females, which is below the average female ratio in the network. Therefore, female receivers are underrepresented. If the advertisements are placed to groups with size at least 40, then among all the receivers, there are over 41% of females, which is above the average female ratio in the network. Therefore, if a recruiting team using such an advertising strategy wants to get a diverse group, they need to consider the group size threshold carefully. And the second application we provide is fact-checking. The spread of fake news in chat networks, especially in end-to-end encrypted networks, has become a severe concern for the society. Right now, different fact-checking organizations have different strategies in terms of prioritizing what to fact-check. Typically, it is based on the combination of importance, relevance, the number of times an individual piece of content has been flagged, and the number of platforms on which it has been flagged. In a highly simplified scenario, will people have an equal tendency to report fake news when they see it? And fact checkers always prioritize to check news with more reports. One could ask the question whether prioritizing based on the number of reports is fair. As news from larger groups is more likely to be checked for reports, the guessing effect implies that relatively to the majority, fake news that spread among minority members might be less likely to be detected and removed. However, the chasm effect shows that this is not necessarily true. We see in the WhatsApp dataset that as the fact checker checks more fake news, the anti BJP goes from underprotected to receiving more protection. For example, if fact checker checks only 20% of all fake news reports it receives, then among all members it protects, there are less than 25% of anti BJP members, which is below the average anti BJP ratio. If instead the fact checker checks 60% of all fake news reports it receives, then among all members it protects, there are more than 28% of anti BJP members, which is about the average anti BJP ratio in the network. Therefore, if the strategy of fact checking uses makes it more likely to check news from larger groups, then the fact checker needs to consider the potential structural bias caused by the network. This is quite important as a seemingly fair strategy can indeed lead to unfairness. That's can this can cause like big damage, especially in things like elections. As a summary, we provide empirical observation from real-world datasets to show the existence of chasm effect. And then we have a simple generative model to explain our observation. Then we have a generalized model which can reproduce real-world social networks. Finally, we provide two real-world applications, job advertisement and fact-checking. That's all for the presentation. I would like to give a special thanks to all of my co-authors. This project is done during the pandemic and everyone has overcome a lot. And now thank you for your attention.